the rest of the class, I want to talk about radiometry, photometry, and color. It's a little bit different than thermodynamics, but it's important for you to understand because so far we talked about measurements in energy, joules, watts, meters squared, and so on. And this is useful as engineers and physicists because that's what we actually measure. Now, imagine you're trying to design something for humans, like when you design lighting in this room, automobile headlamps, or day lighting, right? Some of you are working on. You want to think about the human perception of the light, okay? And then you might want to think in different units because a human being doesn't respond to the photons in the same way as a photodetector does, okay? And that's the difference between radiometry and photometry. And of course, the color is an implication of that. Photometry refers to human-centric light, and radiometry is in the non-anthropocentric light. So, and we'll try to link these. So first of all, let's go back to what we know, which is, first of all, radiometric quantities. Radiation flux is a quantity of energy that's emitted, transmitted, or received per unit time. So if I have a bulb, a certain amount of power going out, you know, it's the amount of the power coming out of such a system is simply the total energy divided by time. The dq or dt if it's changing fast, right? And radium flux is simply units of power, watts. Okay, we're all very familiar with this now. Now, what's, again, as I said before, what's different in photometry is the human element. So how do humans see the light? We don't see it in watts. We see based on the response of the cells in our retina. And that response is very specific to wavelength. And that's shown in this plot here. Okay, our eyes, because we are daytime creatures, have evolved over millions of years such that they have the peak at the same peak as the sun, which is about 550, something like that, green, yellow. So in other words, we can see this the best as you go further away from this peak. The reds are harder to see, blues are harder to see. Of course, this is an average. My eyes, I can't see the reds as good as some of you because I'm older, so it changes with age as well. So something to keep in mind. And then how do you measure this? So we have special units to measure this. So instead of radiant flux, we call it luminous flux. This is the perceived power of light by a human eye, and its units are in lumens. So if you go and buy an LED bulb, its units are not in watts per meter square or watts per meter square per steradian. It's in lumens. So we need to understand what does that mean. Okay. Yeah. So this function, which is plotted here, is also called the luminous efficacy function. And of course, to go between one and the other is simple, right? If I have a spectral response of a source, I can simply take this luminous efficacy function and multiply it by the spectral of the source. Then I will get the response of the eye. Because I have something from the source multiplied by the response of my eye will give me the total response. So I think it's relatively straightforward. Now, we should also be aware that these things change based on the lighting level. It's not a linear response. So I'm talking about the curve here for a second. If the luminosity function can change if you're under low light conditions or nice brightly lit conditions. And you have all probably experienced this when you drive in the dark, before if it's in the dusk, or if you're under broad daylight. So this photopic refers to vision of the eye under well-lit conditions, which is this curve here. The scotopic and mesopic refers to low light conditions, which is a little bit blue shifted and less in the red. So the reds are starting to be very less sensitive. Okay. And we'll see why that's important shortly. Now, the top part here simply refers to how do you go between radiometric flux and luminous flux. If you assume uniform response, a uniform spectrum from the source, you can simply define it as some number here, 683, which turns out to be simply the area under this curve here. Okay, not terribly important at the moment. You don't have to memorize any of this. Times the spectrum of the source in dimensionless units, normalized spectrum source, and this is in lumens per watt. Okay, now let's look at some examples. Oh, actually, I have a simple example here. We just talked about light levels and spectrum and so on. So which street lighting is better for driving? Is it high pressure sodium lamps or metal halide lamps? I don't want to spend too much time on it, but any thoughts? Yes, that's what I would say. So if you look at the automobile headlamps and so on, they're more bluish, cooler white, as opposed to harder white. Right? So as an example. I mean, it's of course very much hand waving. I mean, there's a lot of other things that go into play. But this is a very simple example of why understanding the spectral response under the particular conditions is important. Okay, now if we look at a source again, how do you go from a radiometric quantity to a photometric quantity? If I have a source that emits in a broad spectrum, and there is a spectrum given by this phi of lambda, and now what is spectrum? If you recall, is simply the intensity versus wavelength, right? So we have the solar spectrum, which had some peak at all these things, but it had a peak around the green, yellow, right? So this would be the phi of lambda, or if you can have a lamp or whatever, right? Now I take that and multiply it by the V of lambda, which is my luminous efficacy function, which is normalized with this number here, 683. So I can convert, this is in watts per nanometer, I can go to lumens. So that's how I convert. I have a spectrum in watts per nanometer, multiplied by the human response function, do the integral, and I get total luminous flux, which is a perceived brightness, perceived flux in lumens. Okay, now what is a lumen? A lumen is just a unit, so we have to define it. It's like a meter or watts or whatever, right? So it's defined by some standards authority. It's the unit of luminous flux. It's a measure of the total amount of visible light emitted by a source, but of course, it needs to be more precise than that. This differs from the power since luminous flux takes into account the wavelength sensitivity of the human eye. But first, we need to define a candela. That's this thing right here. Is the unit of luminous intensity. So keep in mind, intensity was watts per meter squared. We need to have a corresponding photometric quantity. Is the power emitted by a source in a particular direction with the spectral sensitivity of the human eye taken into account. Candela is the luminous intensity in a given direction of a source that emits monochromatic radiation of a particular frequency, which by the way corresponds to just green, that peak wavelength I said, not important for us to know, but you should be aware of it. I mean, sorry, you don't have to be aware of it, but just think about it. And the radiant intensity of 1/683 watts per radian. And 1/683 comes from the normalization factor. No need to memorize any of it. It's just a measure of how much perceived brightness is for a given solid angle, given direction. So one lumen, before I do that, one candela is the luminous intensity of one candle. One lumen is one candela times 1 steradian. Steradian being the unit of a solid angle. So we'll see this shortly in an example. Yes, exactly. Green yellow, the peak of the sun. Peak of our response. That's just a definition. I mean, just the standards definition. Yeah. Now, let's think about this for a second. So if I have a light source that uniformly radiates one candela in all directions, so I have a point source, it's emitting in all directions, one candela, then my total luminous flux over the entire sphere, my sphere has a solid angle equal to 4 pi steradians. Then it's simply 1 times 4 pi, or 12.57 lumens. Again, if I have a source whose luminous intensity is 1 candela, that means I'm getting 4 pi steradians out of it. Okay, well, we'll see a few examples. So this particular example here. What is the maximum luminous flux of an LED whose luminous intensity is 1 millicandela? Now, first of all, let's think about what it's asking. Yeah. So I have an LED. I have a luminous intensity of 1 millicandela, which is like my point source here, drawn here, right? Now, what is my luminous flux? It's just 1 millicandela times the full sphere. I'm assuming the LED is emitting into the entire sphere, which is, of course, may not be true, but let's pick the assumption. So the answer is simple, right? Just multiply it. You get that. Worked it out here. Let's say the LED, actually, I assumed that LED emits into one hemisphere, not the full sphere. So solid angle of a hemisphere is 2 pi steradians, half of the sphere. So you take the intensity, multiply it by the solid angle, you get 2 pi, about 6 point something lumens. Is that okay? I went through it a little fast, but I want you to be able to make sure you are following that. We'll do a few more examples. Now let's think about more units, because there are other radiometric quantities we have learned about. What is lux? Lux is the SI unit of luminance or luminous emittance. It's just measuring luminous flux per unit area. Okay? This is equivalent to intensity in radiometric optics. So intensity was watts per meter squared. This is illuminance or lux. So watts per meter squared is equivalent to lux. One lux is 1 lumens per meter squared, or 1 candela per steradian per meter squared. So an example would be, okay, if we want to achieve a illuminance of 500 lux for a home kitchen, what is the minimum required luminous flux from a single fluorescent light? Again, lux, keep in mind, it's the luminous intensity. What does that mean? If I take a meter and measure it at a particular location, I will get one number. And if it's very uniform, I move over and take that same measurement, I'll get the same number. So it's uniform intensity, but it's per unit area. Yeah. So I have these lux meters. So I don't know if you've ever been to a movie studio or a photographer studio. They have this meter that they measure, this lux meter, basically, just to determine the uniformity of lighting the studio or exposure time of your camera or whatever. That's what they measure. So how would we solve this problem? 500 lux. Now we need to think about the different quantities. So you need to achieve 500 lux. What is the luminous flux from a single source? And you have to think about, okay, what is the volume or is the solid angle over which it's being illuminated? So keep it in mind also, and we'll come back to this in a second. A typical LED light puts out 50 to 100 lumens. So I worked it out here. So let the area of the kitchen be 10 meters squared, whatever, some simple number. Illuminance is luminous flux divided by area. A luminous flux is simply illuminance multiplied by area. So illuminance is 500 lux. I know that. The area is 10. So I get 5,000. Now, this is a highly simplistic because I'm assuming that it's completely uniform, which is, of course, not the case, as we will see shortly. But again, I just want you to think about the units and the measured quantities. Okay. Of course, if my area is much larger, like a soccer field, then that A goes up, then I need many more loops, right? Of course, that means I need many more sources. A single source cannot really achieve that. Oops. Now, the equivalent radiometric quantities, again, just to relate back to what we know from before, we have emittance, radiation flux emitted per unit surface area watts per meter square, which is also intensity. So lots of different terminologies there. It's just the flux divided by area. Irradiance in watts per meter squared is emittance is coming from the source. Irradiance is captured by an absorber. That's the only difference. Otherwise, it's the same thing, right? By definition. The corresponding photometric quantities in luminance is units are lux, and intensity is defined as flux per unit solid angle. We saw that before, which is in watts per steradian. So this is the flux divided by d omega, which is the solid angle. Again, I don't need you to understand. I mean, know any of these. I need you to understand. I don't need you to memorize any of these. The corresponding photometric quantity is luminous intensity. So the intensity in watts per steradian is related to lumens per steradian. I think what you need to think about is just on one side, you have the radiometric quantities. On the other side, you have the photometric quantities. Just make sure that you know which one is which. That's the way I would think about this. Now, thinking from the perspective of the source, again, the angle is important and the solid angle is important, because this, where you look at the source, of course, is important, as you will see shortly, because if some sources are directional, like the backlight of your display, if I look at the display straight on, it can be very bright. But if I look at it like that, it's not very bright, right? That's what is meant by the directionality of the source. And this will become important shortly. The size here is also important, which is the extent of the solid angle, right? Because it depends if I have to illuminate an entire room, I need a large solid angle, or am I just doing a spotlight for a museum and I just need a small solid angle? And things to keep in mind. The measurements, of course, the same as before. Radiometrically, it's watts per steradian per meter squared. We've seen this before. Now, let's try to connect it back to the photometric quantity. So if I were to look at a surface, as shown here on this, and I'm looking at an angle theta related to the surface, so that's my angle theta, related to the normal of the surface. And the radiance can be defined as the flux divided by the area that is subtended at that angle, which is dA, infinitesimal area, dA cos theta times, I'm assuming the solid angle is d omega. So what I've done is I've taken this infinitesimal area, projected it normal to it, so that gives me dA times cos theta. Then I'm multiplying it by the solid angle, because that's how much I'm subtending it up. Okay. On the photometric side, you have something called luminance, which is the exact same equation, except that on the numerator, I'm replacing the intensity or the illuminance by visual flux or luminance. Previously intensity, now luminance. Sorry, I shouldn't confuse you. And the units are in candelas per meter squared. Keep in mind, candelas are lumens per radian, right? So, sorry, lumens per steradian. So, lumens per steradian per meter squared. So radiance and luminance can be functions of wavelength. So you can, same as before, so you can define a spectral radiance and spectral luminance, which is similar to what we have seen before, because you have a source, so you do the integral over all the wavelengths. In the case of spectral luminance, you have to use this V. Remember, we have to normalize it at the visual perception function. Luminance is, which is shown here. So the luminance is related to the spectral radiance based on the human perceptual function. So that's just explicitly writing that down. Now, the radiation intensity emitted by an area dA is the flux divided by the d omega, which, if you recall, if I go back here, if I plug this equation back in to this, I get L cos theta times dA. Okay. Now, now I'm going to assume that the radiance is uniform over the area A. So the place I'm measuring this is uniform, so it's very uniform. The total intensity in a given direction is independent of angle. So if I do the integral over all the angles, I get a very simple expression here. I, as a function of angle, is now L of theta multiplied by A times cos theta. Now, what is this? If I have a source, I'm looking at it like my backlight, I'm looking at it at different angles. It varies as A cos theta. I'm going to assume this L is also independent of theta, so I get this expression. And I'm making this simplification. Actually, it should be. This is not there, sorry. The key things are, I'm making this assumption that that's independent of theta. And I'm going to define my naught as L times A. And then I come up with a very, very simple law called Lambert's law, which tells me the intensity of an emitter is also true for reflectors, varies as cosine theta. Just like my backlight. If I look straight on, very bright. As I tilt it, it varies as cos theta. I get to 90 degrees, goes to 0. That's a Lambertian source. Not everything is Lambertian, but many LEDs are. A surface is called Lambertian if it emits or receives radiation with an angular intensity pattern that follows the cosine law. It's only dependent on the projected area. So again, you plot these, create these plots, which you should think about, is on axis, so straight on, I get 100% of the light. As I increase the angle, it goes down, but in a cosine fashion. So it traces out a circle. This is in the positive angle, negative angle, but cosine theta is the same, so you get a circle. Out here, it's 90 degrees, it's 0, right? No intensity, 2% as well. So I think you understand this. A good example of a surface that's Lambertian is it can be diffuse or specular. Specular is simply like a mirror, whereas diffuse is going in all directions. Lambertian reflectors are almost always diffuse. Okay, so diffuse and Lambertian are basically the same for our purposes. The slight difference is not terribly important. And I'll stop here, but I just want to point out one more thing, is that if you, LEDs are of course most of our emitters, like the backlight here, and there are many ways to create LEDs. And the 3 examples shown here, one you can have a planar LED, which is the most common, because that's how you manufacture these using semiconductor technologies, right? When you go buy an LED from Osram or whatever, they usually look like this. And this angle is limited, right? You can't get a emission out from arbitrary angles because of total internal reflection, right? If I have a very large angle here, this refractive index is greater than 1, it will simply get total internal reflected, right? So there is an escape angle within which I can get the LED light out. Now I can change that escape angle. We'll talk about this later on when we talk about light extraction by LEDs. But for now, the way to think about it is I have a specific angle, and if I have a planar LED, I get, which is this curve here, I get a perfect, almost perfect Lambertian emitter, but I can shape it. If I shape it like a sphere, I can get a hemispherical LED. Now, if you think about it, what has happened is that every ray here is at 90 degrees, right? Or 0 degrees, sorry, my incident angle is 0 because it's parallel to the normal. Right? You guys see that. So the light simply just comes out. There's no critical angle. I'm never reaching the critical angle. I shouldn't say there's no critical angle. So that's why it's perfectly uniform. Now I can make it parabolic because I want to make it more collimated. And that's where I get this curve. And that is important for automobile headlamps and things like that. I could shape it either with optics or by shaping this emission device, LED device. Now I'm going to stop here since we're out of time. We'll talk about color next Tuesday. I'll eat a little bit into the midterm review time. But Otherwise, we'll stop here. If there are any questions, let me know. Thank you, and don't forget that we have the presentation on Thursday. I mentioned, the assignment is due today, which is a solution statement. Yeah, right. That's the assignment 4, I believe. Yeah. You can submit on Canvas. I think I put it the submit button now, or send it by email or Slack or something like that. Okay, thanks. And